Math 30-2s, or I'm going to go over this practice exam here. I'll post the PDF as well, so if you don't have to listen to my voice, you don't want to, you can just skip this. So let's just talk about some of these questions about probability. You notice that the first 6 or 7 questions here are all about, like 2 chapters ago when we talked about counting principles. And the reason I do that is because some questions will involve counting principles when it comes to probabilities. And you'll see that like on question 7 in this booklet and question 10 in the booklet as well. Or in this practice here, they involve the counting principle. And actually, oh no, the various boxes also counting principle. Okay. So let's just go through these and just figure this one out. So, because you can change any of these questions to be a probability question. You can just say, what's the probability that my sandwich will have this, this, and this? So you'll just have to know the total number. And to find the total number, in this situation, there are 4 different things here, right? We got the sandwiches, we got the salads, we got the drinks, and we got the desserts. Okay, and then you just say how many choices do we have for each of them, and you just multiply them together. So this is the fundamental counting principle here. So we have 6, we have 4, we have 6, and then we have 3 desserts, and we multiply them all together and get 432. There we go. This kind of pathway kind of question here. Let me just get my cursor in the right spot. Very similar to, say, the fundamental counting principle or to any of the previous ones we've done before. First of all, you want to determine how many possible steps are there. It seems like there's a missing road right here. So there's 1, 2, 3, 4, 5, 6. You always have to take 6 steps to get from this point house to this point here. You always have to take 6 steps, but there's a multiple of different ways. You can go 2 down, 2 over, another down, and 1 over, but they're always going to be 6 steps. Okay? So you like say, have a letter. So you have the word right, 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 down, down, down. So those are my 6 letters in my word. But you notice that there's 3 R's and they repeat. So you got to get rid of those repetitions of both of those letters there because it's 3 R's and 3 D's. You can multiply these out. If you do the math on this, it ends up being 20. Okay. And now I'm going to do a multiplication. I'm going to multiply that with the 1, 2, 3. This word down here, that's just an R, R, and a D. How many ways can I rearrange that? There's 3 factorial, divided by 2 factorial, 1 factorial. Now 1 factorial is not really a number, it's a 1. It's not really that you have to calculate, but if you go through this one, it ends up being 3. You multiply them both together and you get 60 ways out of this one. Now again, that can be changed into a probability question pretty easily, saying, okay, what's the probability that he'll go down, 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 right, 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 down, down, right, right, or right? Like, so let's just take this one path. Well, first of all, you got to know how many possible paths there are. So what's the probability? He'll take this one path here. It'll be 1 out of 60. All right, so all these questions could be easily turned into a probability question. Okay, let's look at this next one here. We're trying to rearrange the letter speak. We did a couple of these probability ones where they just took the letters and spelt it. And this could be, again, what's the probability that they'll have the word speak if SP always end up being the first 2 letters or something like that. So we got to know the proper way to do this. So we have these 2 letters, S and P. Okay, these 2 letters, this is not necessarily in this order, can be rearranged 2 ways. So I'm eventually going to have to multiply things by 2, but they have to be the first 2 letters. So they got to be here at the beginning. My other 3 letters, because there's 5 letters in total, are going to be here. You can go 3, 2, 1, or you can say all of these guys are 3 factorial. So if I go through that, it ends up being 6 times the 2, which ends up being 12 in this case. Those are my 3 other letters. I can get rid of I'll fix that up here so it looks better in the PDF. So it'll be 3, 2, 1. This can just be 3 factorial times 2, if you want to go that way. Okay. This question here, I don't know why I left this one in here. It's just a simple evaluate question. Just punch in your calculator if you want to. If you want to go through the steps, how to reduce this down, you can. But it just ends up being 10 in the end. I just left it in there for accident. Sorry about that. Question 3 and 4, I don't like the way the ABCs are, the choices are there. Like the answer is kind of hidden away of how I would approach this question. But the number of arrangements, that 3 boys and 4 girls in a row, if all the girls must be stuck together. So let's just say all the girls are this big box right here. So there are 4, 3, 2, 1 ways of rearranging the girls. All right, so you can go to the math on this one and say that there are 24 ways to rearrange the girls. Okay. Now it doesn't specify that the boys have to be stuck together. So let's just put the boys here separately. So I got 3, 2, 1. Okay, so there's 6 ways there. It's asking you to figure out of these here, which is the best way to represent this. So right now we have 4 factorial, right, and 3 factorial here. So that's what it looks like. But this is if all the girls were at the beginning. But the girls could be put at the beginning if they want to, or here, or here, or at the end, right? So they could be in any one of those 4 spots between the boys, because the boys could be 1 boy, all the girls, then 2 boys, or 2 boys, all the girls, then 1 boy, or all the girls at the end, or all the girls at the beginning. So there are 4 ways to do this. Beginning, one of the 2 middle spots, or the end. So I have to include that down here too. So I'm going to go times 4. And you look at all these and try to figure out which matches. Is that these 2 will combine together to become 4 factorials. Like just put in the 4 in the front. Oh, just 1 second. Okay, so this ends up being, because 4 factorial times 4 factorial ends up being A up there. Okay. Same thing with question 4. Question 4, they simplified it down just a little bit when they went through this. But let's just figure this one out. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters here. Okay, so there's 10 letters in total. There's a lot of repetition here, so that's why they have all these divide by 2 factorial, 3 factorial things, because there's a lot of repeating letters. But they put a specification here that the first letter must be a K. So the first letter, I have 2 choices for that first letter. Okay? And then for all the other letters, I have 9, 8, 7, 6, 5, 4, 3, 2, 1, which ends up being 2 times 9 factorial. Okay, so that's the top there. If all the letters were kind of unique, that's what it would look like. So what now you're going to do is you have to get rid of all the repetition. So you go through and say, okay, there are 3 A's. So I'll put a 3 factorial there. Okay. There are 2 K's. There are 2 N's. There are 2 S's. Okay, so that's looking very familiar. So this is the A's, this is the N's, this is the K's, this is the S's. Okay. Those are all the repetitions, right? Then what they did here, you notice that none of these answers kind of match here. The B kind of looks pretty close to what it should be because there's something there. There's like a 2 on the top here. A looks pretty close because all the things on the bottom look pretty good. But if you look at this and say 2 factorial, which is just a 2, that's going to reduce out with that 2 on the top. So it ends up being 9 factorial, 3 factorial, 2 factorial, 2 factorial. So it ends up being D in this situation. Yeah, sometimes it's nice also to know when to use permutations and combinations. So like throwing just toppings on a pizza, doesn't matter what order you put those toppings on, they're on the pizza. That's going to be a combination. So remember that permutation order matters. And combinations order does not matter. Okay? Does not matter. So I'm just throwing pizzas on toppings on a pizza. The order doesn't matter there, obviously. For this one here, so you just think about, does order matter? So I'm making a team. I got a little bit of order here because there has to be 1 goalie, 2 defensemen, and 3 forwards. Well, we're going to also assume that like a left defenseman versus a right defenseman, essentially just kind of grouped in together here. So you just go through and say, okay, I have 2 goalies. I had to choose one of them for my team. Then I have 5 defensemen. I got to choose 2 of them. And then I have 10 forwards, and I got to choose 3 of them. All right. So that would make my team of 6. Got 1, 2, and 3. So that makes up 6 altogether. So you just punch these in your calculator, and you get 2, 10, and 120. You multiply them all together, and you get 2,400. Okay. And again, this could be turned into a probability question by just saying, okay, Rick, John, and Bob have to be on the team. What's the probability that they will be picked on the team if they're just picked at random? And then this would be the bottom of that probability calculation, because this would be the total number of teams I could make. And then you have to calculate the total number of teams that will have Rick, Bob, and John on them, depending on what positions they happen to be. Okay, so now we're getting into the actual probability parts here. This is what's more or less going to be on the test. So 5 members of a curling team, of a mixed curling team, include 2 members and 4 males. 4 can only be chosen to play at a time, which makes sense. All males will be on the teams. Okay, so let's figure out how many teams we can make. So we have 5 members, and we can choose 4 of them. So there are going to be a total of whatever number this happens to be. I didn't actually calculate this number for some reason. Actually, I did. It's 5. There's 5 total teams I can make. Yeah. Now, that's probably not going to be true because of positions and stuff, but let's just say they all have equal ability here. But I want to know the probability that all 3 boys will be on this team. So that means I'm going to have C3C. There's only one way to do that. But I need to know there's 2 other girls, so I have to have 2 teams there. Potentially I have all boys and then 1 girl, and then all boys, and then the other girl. Okay, so there are 2 teams I can create there, so it's 2 out of 5 probability that this will happen. What are the odds? If they tell me the odds in favor of her passing her test, what are the odds against her passing her test? You just flip it over and you got 4 over 7. That's a pretty easy question. Same odds here, but now they ask for the probability. So this is where it kind of gets a little tricky here. Remember, define probability. You do the number of favorable outcomes. In this case, it's 7, and you divide it by the total number here. So it'd be 4 plus 7 on the bottom, which would be 7 over 11, which would be 63-ish%, 64%. There you go. This one here, there's a couple of different ways we can do this question. The easiest way to do this question is just think about, okay, how many ways, think about almost fundamental counting principle. Let's assume that's a 50-50 chance of having a boy or a girl. So here's my probability chart. The first kid will be a 50% chance to be a boy. The second kid will be a 50% will be a boy. And the third kid will have a 50% chance of being a girl. This is 1/8. You just multiply the tops, 1 times 1 times 1, and then 2 times 2 times 2 to get 1/8, okay? But that's not the only way this could be rearranged. This would be at the first, second, and third. That's the order it was, but it could just be boy, girl, boy, which will also be 1/8. Or it could be girl, boy, boy, which will also be 1/8. If I add all these together, you get 3/8, which is in terms of percent, because that's what they want in this question. The decimal is 0.37, so this turns into 37.5%. Let me do this one. Another way to do it is you could create a tree. You could do the whole tree way. Maybe I'll show you that. So I'll just put an or here to do the tree way. I got boy, girl, 50% chance of each one of those, so half. And then up here I got a boy, girl, which is another 50% chance for both of those. And then here I got a boy, girl, 50% chance for that. And then each one of these, I have a boy, girl, 50% chance, 50% chance. Boy, girl, 50% chance, 50% chance. Oh, there's a lot of things to write here because there's a lot of different combinations we can have here. It's 50% chance. Okay, now if you were to go through all of these, trying to figure out which ones are two boys and a girl. Two boys and a girl. That's one way. Two boys and a girl would be this one. Yeah. And this one. So there's only three of these, and each one of these, the probability of this one happening, let's call this event A for now, is a half times a half times a half, which is an eighth. And then this would be an eighth, and this would be an eighth. If I add all these together, I get 3/8. There you go. Here's another combination kind of question here. We've got a bunch of kids. They want to go on a trip. What's the probability, in percentages apparently, that they'll be all boys in this situation? So there are 9 boys, and I want to choose 6. That's the favorable outcomes. And then the total number would be, there's 21 kids in total. I need to choose 6 of them. So it's actually like 54,664 different ways I can rearrange those 21 kids. Right? But there are only 84 ways to rearrange all the boys. So it's 84 favorable outcomes out of these total 56 or 54,000. But I'm going to just times this by 100. I'm going to punch in my calculator. Is going to get a kind of decimal here, but you're going to get 0.15%. Not very likely this will happen. What's the probability that Callie, if she tossed all 4 coins in the air, 4 coins in the air, that will land all tails? You could do the same thing we did with the boy-girls one here in the question numerical source number 3. Where rather than boy-girl, it'd be head tails all the way down, but then you would add an extra little piece there. It gets a little bit ugly after a while. So what you're going to do instead is think about how many ways can I rearrange this. So, well, T, 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 T. That's it. T, 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 T. There's no like heads in there. So what's the chances of this? 50% chance, 50% chance, 50% chance. We're going to assume that there's equal probability each way. Get like 1/16, 2 times 2 times 2 times 2, but they're times it by 100%. Get a percentage here. Ends up being 2.25%, or 6.25, sorry, percent. Okay. You can see those are all independent of each other. Like throwing a tail does not change the probability of throwing another tail. Does not change the probability of throwing another tail. So they're independent of each other. Question 13, they're dependent on each other. It changes the probability. Question 13. Let's go to question 12. I've seen question 12 before. To be mutually exclusive just means that they just can't happen at the same time. So multiples of 3, a multiple of 3 is like 3, 6, 9, 12. That's pretty much all the numbers that are multiples of 3 in if you roll 2 6-sided dice and you're adding them together. You notice that 9 is a multiple of 3, so this could happen at the same time. Okay? Same thing like drawing a jack or drawing a face card. They could happen at the same time because a jack is a face card. Right? So if you were like kind of draw a Venn diagram of these two situations, here's my multiples of 3. Here's my 9. They're inside each other, right? 9 is inside this, so this kind of overlaps. So they are not mutually exclusive to each other. Same thing with the jack and the face cards. The jack is inside there. I'm drawing a 2 and a spade. Well, they don't necessarily have to draw 2 spades, but they could happen. So they're definitely not mutually exclusive. This would be more of a Venn diagram that looks like this. Here's my 2 spades. Got spades here, I got 2s here, and there's a little overlap here. So that's the case. And then walking to school, taking a bus, that's definitely mutually exclusive. You do one or the other, you can't really do both. Okay, India here is going to the gym. She has to choose 2 different cardio activities. She has 5 in total. 1, 2, 3, 4, 5 things in total. We're going to assume that she picks them at random and they have equal chance of happening. They don't really specify that, but let's make that assumption. So I want to find the probability of doing the stepper and then running the track at the same time. Okay. This is a formula here. I don't know where my formula sheet went off to. Oh, there it is. Yeah, I want to know when this happens at the same time. Okay. Track. So let's go through the probability of her doing the stepper. Then we're going to times with the probability of going the track if she's already done the stepper, right? So this is kind of, they're dependent on each other. So if I do the stepper, I've changed the probability of the track because there's a 1 out of 5 chance you'll do a stepper to start off with, right? But because I've done the stepper, there's only 4 now for the track, and there's only a 1 out of 4 chance it'll happen because I've done one. I have one less thing to choose from this one. This would be 1 over 20. There's a few different ways to, this is one way to do it. So 1 over 20, if you put that in percentage-wise, is a 5% chance. You could create a tree if you wanted to. You could think of this as the fundamental counting principle, right? She wants to do one very particular thing. She wants to do a stepper and the track, but there are 5 things to choose from here, and there's 4 things for the next thing to do. So it'd be 1 over 20. Kind of like the formula way better for this question. Okay, so the probability that Nathan will do neither of these activities of studying or doing the violin. Let's just imagine this is Monday, this whole box. And there's 2 ways to do this one. You can do it by a Venn diagram, or you can do this by the formula. I'll do both, okay? So the probability that you won't do either one of these things, so I'll just put a little not symbol there. We'll do neither of these activities, and A and B, one being study and one being the violin. So if I did this by the Venn diagram way, I'm going to just start filling in my Venn diagram. One side here is studying. One side is the violin. And then there's a little intersection here for both. So the probability that they'll do both is 0.2. The circle for studying is 0.65. So that means this part of the circle is only 0.45. And the violin is 0.4. So that means this point of the circle is just 0.2. If I were to add all of these pieces together, what I'd notice is that I get 0.85. Okay, but Monday always happens. So Monday is a certainty. Something's going to happen on Monday. So there's a 1.0 chance that Monday will happen. So where's the other piece? Well, that's me not doing anything. So that's at 0.15 there. All right. You could do this by doing the formula way. Say, okay, the formula says the probability of one event happening plus the probability of the other event happening, subtract the probability of them both happening at the same time. Now, the reason I can do this is because I have all this information. Like A, say, is the studying one. B is the violin one. A and B together, we had that number is 0.2. If I did this math, I get 0.85 as well. Okay, but that would be both those things happening, but I want the not one. So I'm going to take 1 minus this number, and I get the 0.15. Okay. Last one here, just another fundamental counting principle question, because maybe you can ask what's the probability that John and Sarah are at the end of the line, right? Well, first of all, I want to find out how many ways I could rearrange these kids for the bottom of the probability, right? Because maybe I can ask that question, but we would have to know what this bottom piece is. But it's not a probability question, so I'm not too concerned about what's on the top. I just want to know, can I get that bottom piece? So John and Sarah are stuck together. They're dating, but they could be John, Sarah, or Sarah, John. So that means I can multiply these by 2, right? So they can be put in 2 different ways. Then I have 3 other friends, right? And these 3 other friends could be 3, 2, 1. So that's 3 factorial. But I can also put John and Sarah here, here, or here. So they can go in one of those 4 spots. So my math here is going to be 3 factorial, those are the 3 kids, times the 2 times the 4. I multiply those together, I get 48. You could have thought of this too. If they're stuck together like a 2-headed monster, there's John and Sarah. Then I have my 3 other friends. I could have said, okay, there's 4 things here, 4 people, 4 factorial ways of arranging them, and then there's 2 ways to rearrange the heads of the monster here. So I can say 2 factorial, or just times 2, which will also be 48. So either one of those 2 ways works out nicely for us, and you get 48. Okay, hopefully that helped you out. If not, come to the meet and ask me a question or 2. That's what I'm here for, right? So I'll see you then. Bye.